Hi everyone, my name is Hilton and this is our project. The team is composed of myself, Eric Greenberg, Joe Poole, Carlos Peralta, and Liz Zahn. Essentially, what we wanted to do is study the roly-poly and also other animals that roll in the animal kingdom. We know that in the animal kingdom, rolling up is often a defense mechanism, so we wanted to ask ourselves the question, will a robot with multiple modes of active rolling increase its ability to reverse over different types of terrain? We started off with the design process. We did lots of initial design sketches to try and figure out the form, shape, and function of our robot. There are many different discussions over who would take what and who would design things, but at the end of the day, we all worked together, collaborated, and developed this CAD model to kind of help us guide what our manufacturing and fabrication process would look like. Many of the interior mechanisms were designed in-house with a 3D printer or via machining. And Eric was primarily responsible for machining a lot of the different metal components, such as the bearings that go into the shell, the central axis, as well as the plunger mechanism that would ensure that the motor box would have enough friction on the inside of the shell to roll the ball, as well as having enough contact with the ground. Then the team got right to work assembling everything. Seen here, Liz and Carlos were primarily responsible for all of the electronics wiring of the robot, and Joe in the back was primarily responsible for all of the different shell mechanisms and how the shell would open and close. We hot wired a lot of the different connectors and sensors to the outside of the shell because we would control our shell and the whole robot with an IR remote for all these different functionality purposes. Alright, this takes us to Experiment 0. Experiment 0 is essentially where we tested all of our different subsystems. This includes testing the motor box, seeing if it will run its turns, testing our DC motors, our different connections with Bluetooth and the IR sensor, as well as testing like the robot's functionality to change between its different forms. This takes us to Experiment 1. Experiment 1 was our terrain mobility test. We tested our robot across 3 different terrains with 3 different forms. The first being the motor box only on the vinyl flooring, the robot in its shell open form on the vinyl flooring, the robot with its shell in its closed form on the vinyl flooring, the robot with just the motor box on outdoor concrete, the robot with its shell open form on outdoor concrete, the shell with its closed form on outdoor concrete, the robot with just the motor box on carpet, the robot with its shell open form on carpet, and lastly, the shell with its closed form on carpet. We ran each trial a number of 5 times for a total of 45 tests. We were able to collect data from the robot's onboard IMU sensor, which allowed us to get both acceleration and gyroscopic data. The graphs generated here for data visualization show the average speed across the length of each test. The solid lines represent the average velocity across all trials, while the dashed lines represent the fastest and slowest runs per robot form. The orange line represents the robot in closed form, the blue represents it in open form, and the green represents it in the motor box only form. From these graphs, we can see that the robot performs fast across all terrain types in its closed form. The closed form also helps it traverse over different types of terrain that its open form can't, such as carpet. However, while the closed form allows it to traverse over much more types of terrain, it is important to note that the robot has much more dexterity and controllability in its motor box only form and its open form. These actually reflect the trade-offs that can be seen in the animal kingdom when organisms engage in ballistic rolling rather than the more controlled methods of transportation. One of the greatest accomplishments of our team was implementing Sense Plan Act via our PID control. It was very hard to get the robot to go on a straight line. However, using the encoders, we were able to implement a simple proportional controller to get it moving straight line. After finishing all of our testing for our robot, we brought it to the Mechanical Engineering Design Expo. There at the expo, we were able to show it off both to our professor, but as well our peers and other members of the mechanical engineering department, as well as those in the tech spark who helped us make this robot happen. In regards to future work, there are many different avenues to explore. These different avenues involve tuning the robot while it's in closed form, applying different materials to our shell for increased versatility, as well as looking at potential different ways that we can incorporate a locking mechanism to have more controlled turns when in its closed form. Overall, this project was very, very fun to work on, and it was a lot of really good experience, both on the research side of things with testing hypotheses and the mechanical fabrication side of things by building a robot. We all really enjoyed working together, and it was a great experience. Thank you, Dr. Webster Wood, for leading such an awesome class, and I hope everyone has a great summer. Thanks!